Hello students, so in last class we discussed about adiabatic process and even polytropic processes and non-polytropic processes and how to calculate the molar heat capacity of those processes, right? Okay, so today we'll start off with how to identify an adiabatic process and an isothermal process on a PV graph. Clear? So when we draw a PV graph for these two processes, they look identical. So both of them will look like curves. You know that isothermal process will look like a rectangular hyperbola. It is a rectangular hyperbola, right? So which would be a curve like this. Yes or no? Even adiabatic process will also look in the same manner, because the process equation for isothermal process is PV is equal to constant, and process equation for adiabatic process is PV power gamma is constant, right? So both of them, this gamma is basically either 1.4 or 1.33 or 1.67 depending on what type of gas it is, correct? So these two curves will look almost the same, just the shape will look like the same, so it will be little bit difficult for us to identify which one is which unless and until we know few more concepts regarding that. Clear? So which is what we are going to discuss now, right? So first of all, so let me draw those graphs for you. So let's say this is a state from where I am taking a gas in an isothermal process and adiabatic process, right? So both the processes will look like this curve itself, but we don't know which one is which. So I am telling you one of these is an isothermal process and one of this is an adiabatic process. We need to identify which process is which. Clear? So for that, what I'll do is I'll just look at this particular expression, and you can clearly see that from these two graphs the shape looks identical. Only the thing is that one is more steeper, this curve is more steeper, and this curve is not so steep. So I have to differentiate between them, between which one is more steep and which one is more flat. So that is the concept that I'll be using here, right? And steepness of a curve can be understood by looking at the slope of the graph. Yes or no? So from these two, what I'll do is first I'll consider the adiabatic process, because this is a PV graph. So I'll take the adiabatic process and I'll calculate the slope of adiabatic curve on a PV graph. Clear, students? So we know that if I have to find the slope of a PV graph, I need to find dP by dV. Slope of this is nothing but dP by dV, right? And to find dP by dV, I'll just differentiate this expression. Clear, students? So when I differentiate, I'll use UV rule. So P into gamma times V power gamma minus 1, correct, into dV plus V power gamma into, now I'll differentiate P, so which gives me dP is equal to 0, correct? And now I can cancel out V power gamma minus 1 here and V power gamma minus 1 here. I'll be left with V, correct? And I need what? I need dP by dV. So I'll send this dP that side. I'll get minus of VdP is equal to, what do we have here? Gamma P dV. Gamma P dV, correct? So if I find dP by dV, I'll get dP by dV for an adiabatic process is equal to minus gamma P by V. This is gamma, right, students? So this is the expression that I got. So the slope of an adiabatic curve can be calculated by using this expression, minus gamma P by V. So P and V will be changing continuously. So as P and V values are changing, we can say that the slope will also be changing. And the minus sign here indicates that the slope of the curve should be negative. Yes or no? Because wherever you draw a tangent to these curves, it will anyways make an obtuse angle with the positive x-axis. So that is not a problem. So that is the reason why we have a negative sign here, right? So by looking at the magnitude of gamma P by V, we can understand the magnitude of slope. Clear, students? Okay, so if this is the slope of adiabatic process, what is the slope of isothermal process? So let's do a similar analysis for an isothermal process as well. Clear, students? Okay, so the process equation for isothermal process is PV is equal to constant, and once again using this I'll find the value of dP by dV for an isothermal process. I'll differentiate this expression. So what I get is P into dV plus V into dP is equal to 0, right students? And when I rearrange the terms, because I need dP by dV, so I'll get dP by dV is equal to minus of P by V. So if you rearrange and evaluate this, this is what you get, and this would be the slope of an isothermal curve, right? So now look at these two results that we have derived now. So in one case we have the value of dP by dV, which is the slope of an adiabatic curve, as minus of gamma P by V, and the slope of an isothermal curve is minus of P by V, which means the slope of adiabatic curve is gamma times the slope of isothermal curve. So let me write that. Slope of an adiabatic curve is equal to gamma times slope of isothermal curve, right students? So that is the result that we are getting here. So what this means is, if you keep away the negative sign in both the cases indicate that both are having an obtuse angle, both the tangents would be making an obtuse angle, but which one is more steep, which one is more vertical, is decided by which one has more magnitude, right? Out of these two parameters, which one has the most magnitude, this or this? Forget about the negative side. So the one with more magnitude is this, because gamma is greater than 1. Yes or no? Because gamma is greater than 1 for any gas, we can say that this value will be greater than this value. So which means if I consider this point where both the curves are meeting with each other, at this point P by V values will be same for both. Yes or no? Because both the curves are passing through that point. So at that position, so whichever curve has the greatest slope is the adiabatic curve. Is that clear? So out of these two curves, we can clearly see that this is the one with the more slope at this point. Clear? I'm talking about the magnitude of slope. This will have a larger magnitude of slope. So the tangent drawn to this will be like this, whereas the tangent drawn to the upper curve would be something like this. Yes or no? So because this one is more vertical, we can say that this one will have a more magnitude of slope. So this is more steeper, and the one which is more steeper is the adiabatic curve. So this would be the adiabatic curve, and this would be the isothermal curve. Clear students? So don't remember it like isothermal curve should be higher and adiabatic curve should be lower. Don't remember like that, because if I just extend this further, if I just extend these curves further, so the isothermal curve would be like this. So it would be something like this, right? Whereas the adiabatic curve would be the extension of this curve, and the extension of this curve would be something like this. Yes or no? So yeah, something like this. If you remember like this, that isothermal should be above. If you see here the isothermal curve is below the adiabatic curve. This whole thing is the adiabatic curve, right? So let me darken this further. So what I am drawing darker is basically our adiabatic curve. So yeah, this is our adiabatic curve. Thicker curve is the adiabatic curve, and the thinner curve is the isothermal curve. I hope this is clear, students, right? So adiabatic curve is the one which is more steeper, right? And the one which is more flatter is the isothermal curve. That is how you should identify, not by remembering it as the one above and the one below. So that is a wrong way of understanding or identifying the curves. Clear? Okay, so that is the idea. So wherever they are meeting with each other, at that point we can say that the one which is more steeper, the one with more slope, is the adiabatic curve. Clear? Okay, now based on this, let us consider a theoretical question. Clear? So let's say on a PV graph, right? A gas is expanded from an initial state to a final state where it is having double the volume, let's say, through three processes. First process is isobaric. So first process is isobaric, second process is isothermal, and the third process is adiabatic. So if a gas is expanded through three processes, clear, to double its volume, which means, let's say, this is the initial volume of the gas, which is V naught, and this is the final volume of the gas, which is 2 V naught, and initially the pressure of the gas is some P. Clear? So this is where the initial state of the gas is represented. Now what we are doing is we are doubling the volume. You know that to double the volume, I can have many processes to double the volume. I can have a process like this, I can have a process like this, a process like this. There are many processes. So we are considering these three processes. So let's say the work done in this isobaric process is W1, isothermal process is W2, or let's say isobaric is IB, and work done in isothermal is IT, and work done in adiabatic process is AB. Clear? So these are the work done in different processes. Now we need to compare them, which one is greater and which one is lesser, right? So the idea is pretty simple here. You don't have to like write any equations and solve also. Just draw the graphs, PV graphs of each of these processes. So in an isobaric process, starting from this state, we need to reach this volume, right? So which means you have to reach some point on this line. Yes or no? So all the points on this line will have a volume of 2V. So first I have to reach from here to this line isobarically. Isobarically means constant pressure, right? So this would be the first process, isobaric process, right? So we are going to reach this state. Now second process is an isothermal process, and the third process is an adiabatic process. We know that both would be curves. So one process would be like this, the other process would be like this, and just from what we have discussed earlier, the one which is more steeper is the adiabatic process. So we can say that this would be isotherm and this would be the adiabatic. Clear, students? So now I have drawn all the three processes, isobaric, isothermal and adiabatic, on a PV graph. Clear? Now by just looking at the graph, I can tell which one, in which process is the work done more, because area under the graph represents the work done. So area under the graph is greater for 1, followed by 2, followed by 3. So we can say that work done in isobaric process will be greater than work done in an isothermal process, and that would be greater than work done in adiabatic process. Clear, students? So yeah, that is how we can compare, right? So they can also ask you questions based on compression also. They can say that, let me ask you a similar question. I want you to answer this. Let's say the gas is taken from this initial state. So from this initial state where the volume is V naught, it is taken to a state where the volume becomes half, which is V naught by 2. Clear? So here the volume is V naught. So initial state the volume is V naught, and in the final state the volume is V naught by 2. So from this state you need to reach this state somewhere on this line, clear, where the volume is half, and you can reach by the three processes which I have just mentioned. You can either reach from here to here isobarically, or isothermally, or adiabatically. Clear? So this time I want you to compare work done on the gas. Work done on the gas. So in which process are we doing more work? Will it be the same order? Are we doing more work in isobaric process? So this time remember we are compressing the gas. So from here, so you know that one process would be like this, isobaric process would be like this, and the other two processes would be like this. And I want you to identify which one is which out of these three, and I want you to compare work done on the gas during compression via these three processes. Clear, students? So please write the order in the same way. Clear? Okay, students, now we'll discuss about conversion of graphs, right? So if they give you, if they represent a process in a particular graph, and they ask you to draw or represent the same process in a different graph. So how do we convert a process in one graph to another graph? Clear? So yeah, let's discuss about that. So we'll start off with a simple case where we have, let's say, a PT graph given to us, okay, and PT graph is given like this. So let's say this is our initial state A, B, C and D. Okay, so this is the process that we are taking the gas, right? So from this initial state, the gas is basically taken through these four processes and brought back to the same initial state. So such processes where the gas returns back to its initial state, we call them as cyclic processes. So we'll discuss in detail about cyclic processes later. So we have a separate topic where we discuss about this. For now, we'll just try to convert the graphs. Clear? So now let's say we need to convert this graph into a TV graph, or even a VP graph. Let's say we need to draw this as a VP graph, V versus P. Okay, a VP graph. Okay, fine. So the idea here, see, whenever you are trying to convert a graph, so please remember these 2 points. The first point is the shape that you have to draw. Clear? You need to decide upon which shape of the graph should I draw. So that is the first point that you'll have to think about. And the second thing is the direction in which you have to draw. So I'll explain you what these 2 points means. We'll apply this in this conversion now. So first of all, let's go from A to B. Now A to B, you can see that A to B is basically a constant temperature process, and a constant temperature process, how does it look like on a PV graph? So it looks like a rectangular hyperbola, right? Whether it is a PV graph or a VP graph, constant temperature process will look like a rectangular hyperbola, yes or no? So yeah, let me draw a rectangular hyperbola like this. So let's say this is A, this point state A. Now that rectangular hyperbola which I have to draw, I have decided upon the shape. I have decided that what I should draw from A to B is a rectangular hyperbola, right? Now from A I can draw a rectangular hyperbola like this to reach B, or I can draw a rectangular hyperbola like this to reach B. So that is what the second point is. We have to decide upon the direction in which I have to draw. Should I draw it like this to reach B, or should I draw like this to reach B? Okay, let us analyze that. So what I'll do is I'll draw it in some direction. So let's say I have drawn it in this direction to reach B. I don't know whether it is correct or not. Let us verify. So as I go from here to here, from A to B, for verification what you will do is you just look at what is happening to this other parameter. What is happening to the pressure as I go from A to B? So you can see that the pressure is increasing in that process. Yes or no? Even though the temperature is same, as I go from A to B, the pressure is rising. So you'll also have to draw it in the same manner. This is a hyperbola, rectangular hyperbola, meaning that the temperature is constant, but you should always move towards increasing pressure. So that's why we have drawn it towards this side. Is that clear? If it was the reverse, then you should have drawn the graph towards this side. Clear, students? So that is how we decide upon the direction, right? So A to B, the pressure is increasing, so it should be drawn in this manner. Now B to C is a constant pressure process. So B to C, a constant pressure means here it is a horizontal line, here constant pressure means vertical line. So now I have decided upon the shape. So the shape of the graph from B to C should be a straight line, vertical straight line. So should I draw it upwards or should I draw it downwards? is what I have to decide next. Yes or no? So shape is decided, we have to decide the direction. Upward straight line or downward straight line. So for that, see what is happening here to the temperature. As I go from B to C, what is happening to the temperature? Temperature is increasing, right? So if I write PV is equal to nRT, so as I go from B to C, pressure is constant. So pressure is constant and temperature is increasing. Temperature is increasing, which means volume should also increase because pressure is constant. V and T are directly proportional. So volume should increase. So the straight line which you should draw should be in such a way that the volume increases. So from V towards higher volume. So C will be somewhere over here. Okay, students. So that is how we should draw. Maybe a little bit higher or not even higher. So C will be somewhere over here. I'll tell you why I have drawn it like this, why I have stopped it here itself, why have I not drawn till here, you'll understand in a while. So B to C, I have drawn the graph, clear? Now C to D. So C to D is once again a constant temperature process, and once again it should be a rectangular hyperbola, right? So it should be a curve, so which means I should once again decide whether I should draw that curve like this from C towards right or from C towards left. So C to D, pressure is decreasing, so very simple, go towards decreasing pressure, that's it. So from here I'll go towards decreasing pressure. Clear, students? So this is where D should be, and before I mark D, let's also look at the final process. So D to A is a constant pressure process, which means I should have a vertical line once again, so a vertical line again, right, students? So this is how the cyclic process looks like after you convert that into a VP graph. Clear, students? So this is how it is. Now I told you earlier that I will tell you why I have stopped this graph here itself, why I haven't taken it till here. So B to C, why I could have drawn it till here and then I could have drawn an isotherm like this, right? See, the reason is, if you look here, see, I've told you earlier, in a PV equal to nRT expression, if I have to find volume, so in this is a PT graph. In a PT graph, you know that P by T will represent the inverse of volume. So now if you look at A and C, so point A and point C, it looks like from the graph which I have drawn, it just appears to me, right? You can clearly see also that a straight line drawn from origin to A and a straight line drawn from origin to C are very close to each other, right? Or it might even be the same straight line. I have drawn it in such a way, they are very close. So whatever line I have drawn from 0 to A and even 0 to C, they are almost close to each other. What that means is P by T values for A and P by T value for C is same or very close, yes or no? Which means volume at A and volume at C are also almost close to each other, and that's the reason why we know that volume at A is this much. So volume at C should also be closer to the volume at A. So that's why I have stopped the graph at this position itself. I should not take it till here because here the volume at C will be greater. You understand that? So that is just a rough picture of how we should draw the graph. Clear, students? So but the first thing or the two important points that you'll have to keep in mind are these two. So as long as you are checking these 2 points every time, so you'll not make any mistakes, right, students? So let's see one more example. So this time, let's say we have a VT graph given to us, and the VT graph is like this. Okay, so this is how the VT graph looks like. So this is A, B, C, D. Okay, now we need to convert this, let's say, into a PV graph. or you can draw anything. You can also draw a TP graph if you want. Okay, let's draw TP, T versus P. Yes, students. Okay, first of all we need to decide upon what each line here represents. So A to B, right? So what type of process is A to B? You can see that A to B is a straight line which is passing through origin. So which means V by T is constant for this whole process. Yes or no? So for any point on this, you can say that V by T will be same, and V by T is same means what? Pressure is same. So A to B is a constant pressure process, right students? And constant pressure process, let's say I draw A somewhere over here. So constant pressure process is a vertical straight line in this graph, yes or no? And direction, how do I draw that? A to B, volume is increasing, temperature is increasing. So from A to B, temperature should increase. So I should draw it upwards. If A is here, B will be here. So A to B is done. Now B to C. B to C is a constant volume process, right students? Okay, so how do I draw a constant volume process in a TP graph? So PV is equal to nRT. So constant volume. So if volume is constant, it means P is directly proportional to T. So P and T are directly proportional to each other, which means it is in the form of Y is equal to mx. Yes or no? So which means it should be a straight line passing through origin. So B to C should be a straight line which is passing through origin like this. So C should be somewhere on this line. Yes or no? Should I draw C on this side or this side? Which means from B, should I draw the process towards this side or towards this side is the next question. So direction is what we have to decide. Now B to C, temperature is increasing. So which means from B to C you should move towards increasing temperature. So C would be somewhere over here, let's say. This is where C is. Now C to D is basically a constant temperature process, and constant temperature process, okay, how does it look like on this graph? It should be a horizontal line, yes or no? Constant temperature process should be a horizontal line. So from C I'll draw a horizontal line. So I can draw it towards left or I can draw it towards right. So what should I draw? So what is happening as I go from C to D? Volume is decreasing, yes or no? So I should draw it in such a way that volume decreases, correct? So in a PV is equal to nRT expression, once again, temperature is constant and volume should decrease. Temperature is constant and volume should decrease, which means pressure should increase, yes or no? So I should draw D somewhere over here on this line. Clear students? I hope this is clear. So from C to D, please look once again. As I go from C to D, volume is decreasing. At constant temperature, if volume decreases, pressure should increase. Pressure is increasing. So this is where D would be, correct? Now finally D to A is a constant volume process. So constant volume process, as I told you once again, constant volume process in a P versus T or T versus P graph should be a straight line passing through origin, yes or no? So just draw a straight line passing through origin which passes through both A and D. So you'll have a straight line like this. Let me just redraw this position of A. So you'll have a straight line like this passing through origin as well as A and D. So this is A, this is D. So the process would be like this. Okay students, so this is how this cyclic process looks like on a TP graph, right? Simple, right? All you need to do is just check these two each and every time and you won't be making any mistakes, right? Okay, so when it comes to these graphs, sometimes they won't give you the basic parameters like P, V, T. So sometimes they'll give you parameters like U. internal energy, or they can also use rho. All what you need to just keep in mind is whenever they give u, just think of it as t, because u is directly proportional to t. So no, so if they give you a graph between internal energy versus volume, it means that they are giving you the graph between temperature and volume. So please keep in mind that internal energy is directly proportional to temperature. So wherever they are giving you u, you can just replace it with t to analyze the graph. And whenever they are giving you rho, you can directly understand that rho is inversely proportional to volume. Yes or no? So rho is inversely proportional to volume. So wherever they give you rho, just replace that rho with 1 by v. So what I mean to say is, for example, let's say they have given you a graph like this. So let's say on the y-axis we have rho, and on the x-axis we have p. Clear? And the graph that they have given us is a straight line passing through origin like this, and they're asking us to tell which process is this. So we have a straight line which passes through origin. So if a gas is taken from state A to state B in a process represented like this, rho rho versus P graph in this manner. So what is this process? Okay, so the idea is once again understanding this rho as 1 by V. So they have basically given us a graph for 1 by V versus P, correct? So 1 by V versus P graph is given to us. So this is 1 by V and this is P, and it is a straight line passing through origin. And you know that whenever we have a straight line passing through origin, we can write it as y is equal to mx. So y, which is 1 by V, is equal to mx p, which means 1 by V is directly proportional to P, right? So this basically represents 1 by V is directly proportional to P, which means PV is a constant. So no, 1 by V is directly proportional to P implies PV is a constant. So what they have drawn here, although it may not appear to be that, but it is an isothermal process. So it is an isothermal process. So they can give you questions like this. They'll give you a graph like this for rho and P, and they'll ask you what is the change in internal energy between A and B. So it is 0 because there is no change in temperature. A and B will have the same temperature. In fact, each and every state on this process will have the same temperature because it is an isothermal process. Clear, students? So wherever they give you rho, please understand it as 1 by V. Wherever they give you U, understand it as T. Right, students? Okay, students, now let us discuss about a cyclic process. So cyclic process generally looks like this. If you draw a PV graph for it, so the gas starts from an initial state. It goes around different processes like this. It could be some random processes like this, and then it returns back to the initial state once again. The gas is brought back to its initial state. So if this is the initial state, so the gas is taken around in different processes like that, and it is brought back to its initial state. So any process that looks like a closed figure on a PV graph, it is what we call as a cyclic process. Clear? And you know that in a cyclic process, because the gas is returning back to the initial state, there is no change in temperature. So delta T is 0, and this would imply that the change in internal energy is 0 for a gas in a cyclic process. So during this process, as let's say there are multiple individual processes here. Let's say this is process 1, this is process 2, so on. There might be multiple other processes. I am only drawing a few here, right? There are n such processes, let's say. So in all these processes, there will be some change in internal energy here, there will be change in internal energy here. Similarly, there will be change in internal energy in each and every process throughout that cyclic process, for each individual process there will be a change in internal energy, but when you add all of them to find out the total change in internal energy, by the time it reaches back to the initial state, that would be 0. So what I am trying to say is, so let's say this is 1, 2, 3, so on, n such processes. So for the first process, I can write delta Q1, heat supplied in this process, is equal to delta U1 plus W1, correct? Similarly, for the second process also I can write delta Q2 is equal to delta U2 plus W2, and so on. This same thing repeats for each and every step in that complete process. And when I add all these terms, I'll have sigma of all the delta Q's is equal to sigma of all the delta U's will be equal to 0. So this whole term, so this whole sum will eventually become 0. Clear? That is what is the basic definition of a cyclic process. Because it is returning back to the initial state, it means that there is no change in internal energy. Plus, this whole thing basically will be the net work done by the gas. Clear, students? So this is one very important result that we can say about a cyclic process. In a cyclic process, the net work done by the gas in that cyclic process can also be written as sum of all the heat exchanges. Clear? So I'll write that statement: net work done is equal to sum of all heat exchanges. Dear students, when you add all the delta Q's, whatever value you get here, whether it is positive, negative, whatever it is, just add all the delta Q's for each and every process, and when you add all of them, whatever you get will be the work done in that cyclic process. And one more very important thing that we can say about work done in the case of a cyclic process. So let's say we have a PV graph like this, and we are given a cyclic process. Let's say the process is something like this. So one process is like this, and another process is like this, and the third process is like this, let's say. So let's consider a process like this where this is state A, B, C. So a cyclic process like this. Now if I need to find the work done in a cyclic process, so you know that for finding out work done we generally use area under the curve, right? So even in this scenario, to find the work done in this cyclic process, I'll first take this step, find the work done in that step, which will be area under the curve, yes or no? So which gives me this complete area. So this complete area will be the work done in process AB, yes or no? In the same manner, if I consider process BC, so in process BC, area under that curve will be this area. So this area here will represent the work done in process BC, right? And you know that work done in AB is positive because volume is increasing. Work done in BC is also positive because volume is once again increasing. So both AB and BC, the work done is positive. Now when it comes to CA, process CA, C to A, which is this process, we know that the work done is negative because volume is decreasing, and I'll draw it like this. So area under that curve will be in this manner. As you can see here, the negative work that is being done in C to A is cancelling out some part of the work done during process ABC or AB and BC. Yes? So whatever net work that is done during the process will be only the area inside the curve or inside the cycle. Yes or no? So whenever you are required to find work done in a cyclic process, work done in a cyclic process will be equal to area enclosed within the PV graph. Within the PV graph. Clear? So that is how we evaluate the work done in a cyclic process. And one more important thing that you'll have to keep in mind here is that this work done which I have here is a positive work done, because when we initially calculated the work done, So work done during AB and BC was positive work. So simply put, what you can remember this as is that whenever we have a clockwise cycle, so this is a clockwise cycle, right? So in a clockwise cycle, work done will be positive, and in anti-clockwise cycle, work done is negative. And the reason is pretty simple. See, in clockwise cycles, whatever part of the graph which is on the top, the volume will be increasing, and whatever part of the graph which is at the bottom, the volume will be decreasing. So the top part, more work will be done, more positive work will be done, and less negative work will be done. So eventually the total work done will be positive. Similarly, if you take an anti-clockwise cycle, at the top volume will be decreasing, at the bottom volume will be increasing. So which means net work done will be negative in that scenario, right students? So yeah, these are some points which you have to know. Clear? So now what we'll do is we'll take a question and we'll try to find out the work done in that process by using both the methods. One method is by finding out area enclosed within the PV graph, and the other method is to find the work done by adding all the heats in each and every process. So we'll use both the methods to find out work done in a cyclic process, right? So let us take a scenario like this, where we have a PV graph given to us. A gas, a monoatomic gas, is undergoing a process which is given like this. So let's take a process which is in the shape of a rectangle. So this is how the process is. So let's take some values. The pressure here is P naught. The pressure here is 2P naught. Volume is V naught, and the volume here is 3V naught. Right students? So we have a process like this. So this one is a vertical straight line. So we have two vertical straight lines and two horizontal straight lines. You can understand that two of them are constant pressure processes and two of them are constant volume processes, right? Okay, so now we need to find out the work done, correct? So first of all, the pretty easiest way is to find out area enclosed within the curve. So we can write down net work done in this process is equal to the area which is inside this curve. And how much will this area be? It is nothing but the area of the rectangle. This is P naught, 2P naught minus P naught is P naught. This is 2V naught, 3V naught minus 2V naught is 2V naught. Yes. So 2V naught into P naught will give me 2P naught V naught. That is the work done during this process, correct? So what we will do now is, let us try to find out that value by using the sum of all heats. Clear? So what I will do is I will call this as process 1, this as process 2, 3 and 4, and I will find the values of Q1, Q2, Q3, Q4 and add all of them. Clear students? So let's start off with Q1. So Q1. So the gas is taken from this state to this state, and you can clearly see that this is a constant volume process, and in a constant volume process, heat supplied delta Q will be equal to NCV delta T. Yes, because this is a constant volume process. So NCV delta T, and because I have taken a monoatomic gas, this value can also be written as 3 by 2 NR delta T. Correct students? 3 by 2 NR delta T, and you know that NR delta T, for any case we can write the value of NR delta T as 3 by 2 times delta of PV. This is a very important way that you should understand, important method that you should understand. So NR delta T, the value of NR delta T is delta PV, which means change in PV. What I am trying to say is, see, NR delta T means NR T final minus T initial, correct? Now NR T final means P final V final, and NR T initial means P initial, V initial. So I am calling this term PV final, PV initial as delta PV. Clear, students? So this is what we can understand it as. So now substituting the values, I get 3 by 2 times, what is delta PV? What is final PV? So final pressure is 2 P naught, final volume is V naught. So 2 P naught V naught minus initial PV. Initial pressure is P naught, initial volume is V naught. So initial PV is P naught V naught. So simplifying this will give me the value as 3 by 2 P naught V naught. That's it. Correct? So that is the value of delta Q1. Now similarly, let's calculate delta Q2. Now delta Q2 for this process, this is a constant pressure process, and you know that for a constant pressure process we write this value as NCP delta T, and NCP delta T, Cp value is 5R by 2 for a monatomic gas, so I can write this as 5 by 2 NR delta T, and just like we have discussed earlier, NR delta T can be written as 5 by 2 times, this can be written as 5 by 2 times delta PV, which means P final V final minus P initial V initial. Okay, let's substitute the values. So this should be equal to 5 by 2 times, for this process, what is P final V final? So at this state, final pressure is 2 P naught, final volume is 3 V naught. So which means the product will be 6 P naught V naught. So 6 P naught V naught minus, for this process, what is initial P naught V naught? I mean initial PV, 2 P naught into V naught. So 2 P naught V naught, right? So minus 2 P naught V naught, and this on calculation will give us 4 by 2, which is 2, 2 into 5 is 10. So 10 P naught V naught. Right, students? So that is delta Q2. Now similarly we can calculate delta Q3. So heat supplied during this process, correct? So this process is once again an isochoric process. So what I'll do is I'll directly use this result. Isochoric process can be directly written as NCV delta T, which means 3 by 2 times delta PV, correct? So when I substitute the values, I would get 3 by 2 times, for this process, final value of PV is P naught into 3 V naught. So 3 P naught V naught minus initial value is 2 P naught V naught into 3 V naught, which is 6 P naught V naught. So into 6 P naught V naught, and solving this will give us how much? 3 by 2 into minus 3, which is minus 9 by 2 P naught V naught. So that is delta Q3. Now similarly, delta Q4. So delta Q4. So this is once again a constant pressure process, right, students? So constant pressure process, so we can say the heat supplied will be 5 by 2 times NR delta T. So I can write it as 5 by 2 times NR delta T is delta PV. So for this process, final is P naught V naught. So P naught V naught minus initial is P naught into 3 V naught. So 3 P naught V naught. And solving this, we get, this is minus 2 P naught V naught by 2, which gives me minus 5 P naught V naught. And that's it. Right, students? So we have all the 4 heats now. And as I told you, according to what we have discussed earlier, in a cyclic process, sum of all the heats will be equal to net work done, right? So let's calculate the net work done. So W net is equal to, just add all the delta Q's, whether they are positive, negative, just add all of them. What do you get? So here P naught V naught is common. So P naught V naught into, we have a 3 by 2 plus 10 minus 9 by 2, minus 9 by 2, minus 5. So how much would this be? So this is how much? If I take LCM, we'll have 20 plus 3, 23, 23 minus 9, 14, 14 minus 10, 4, 4 by 2, which is 2 P naught V naught. So which is exactly same as what we got earlier, right, students? So yeah, that is the expression for net work done. Clear, students? And here we'll be defining another very important parameter associated with a cyclic process, which is basically denoted with an eta, and it is called as efficiency. So efficiency of a cyclic process. So generally efficiency basically means output by input, right? So output by input, correct? So generally in a cyclic process we define output as the work done by the gas. Whatever work the gas does during that process is what we call as the output. So work done by gas is the output, divided by input is the heat supplied. Heat supplied. So to extract work done from the process, from the gas, we are giving some heat, yes or no? So we'll be learning in detail about this kind of cyclic processes later during second law of thermodynamics. Clear? So for now, just understand that for a cyclic process, whenever you have to define efficiency, efficiency basically is defined as output by input. Output is the output is the work that we are extracting from the gas. What is the work done by the gas is the output for us. Clear? And to extract that work, we are giving some heat to the system, right, to the gas. So that input heat given is what we call as input. Clear? Now for this process that we have just discussed, we can calculate the efficiency as work done. What is the work done by the gas throughout this process? Is 2 P naught V naught. So 2 P naught V naught divided by how much is the heat supplied to the gas. If you look at that, heat is basically supplied during two processes. We are supplying heat in this process and we are supplying heat in this process, because as you can see here, delta Q's are positive here and here. All the others are negative. This is negative and this is also negative. So in two processes out of these four, in these two processes you are supplying heat. In 1 and 2 you are supplying heat. In 3 and 4 you are removing heat. Yes or no? You are taking, the gas is rejecting the heat. Yes or no? So to extract this much amount of work, 2 P naught V naught amount of work from the gas, how much heat was supplied by you is what you have to put in the denominator. Clear? So which means the amount of heat that was supplied by me is this plus this. Correct? How much is that? P naught V naught, if I take common, I'll have 10 plus 3 by 2. So 10 plus 3 by 2 times P naught V naught. And what is this value here? P naught V naught gets cancelled. 2 goes to the numerator. 20 plus 3, 23. So this would be 4 by 23. So this term here is what we call as efficiency. If they are asking you the efficiency in percentage, just multiply that with 100. Clear, students? So yeah, that is what we mean by efficiency of a cyclic process. You will understand why we are defining, why we are calling it as outputs and inputs. What is the meaning of why are we talking about efficiency of a cyclic process? What is the physical meaning of it? So you will understand that when we talk about something called as a heat engine. So heat engine is basically a device which converts heat into work, heat energy into mechanical work. Mostly all the vehicles that we use, petrol engines, diesel engines, they're all heat engines basically. So we create heat inside the engine and we convert that into mechanical work. Clear? So how much amount of heat given by us was able to get converted into work is what we understand during this process. Clear? So the meaning of this efficiency means how much heat was given by me to extract a particular amount of work. So work extracted divided by heat supplied is what we call as efficiency. Clear, students? So yeah, for any cyclic process, this is the method. So if there are any individual processes in that cyclic process, in each and every one of those individual processes, find the delta Q's. Clear? Find all the delta Q's. In the numerator, you will add all the delta Q's. Positive, negative, you'll add all the delta Q's in the numerator to get work done. In the denominator, you'll only write the positive delta Q's. Clear? You can also keep that in mind like that. So if I have to write the expression for efficiency, let me write it like this. Okay, I'll write it in the next board. Okay. Okay, students. So what we have discussed till now is this expression. So efficiency of a cyclic process can be written as sum of all the delta Q's. When we add all the delta Q's, we'll get the net work done, which can also be sometimes calculated by using area inside PV graph, right? Divided by this is heat supplied. Correct? Okay then. So now I have a question here. So the graph given here is for temperature versus volume. So obviously you cannot calculate area under the curve now, right? So we have 4 different states. This graph here is basically a rectangle, which means these vertical lines are constant volume processes, these horizontal lines are constant temperature processes. Clear? So once again you can consider this as process 1, process 2, 3 and 4. So you can find out delta Q1, delta Q2, delta Q3 and delta Q4. Right, students? And we have discussed just earlier how to find delta Q's for a constant volume process, NCV delta T, right? So similarly, try to find out what is delta Q for constant constant temperature process. The delta Q is same as work done for a constant temperature process, right? So I want you to find all the 4 quantities and evaluate the efficiency of this cyclic process. Clear? So that would be a work for you. So we can discuss this in the next class. Clear? And with this we'll end today's lecture, and in tomorrow's class we'll solve some examples based on thermodynamics.